The beginning of the chapter, we talked about the Arrhenius definition and the Bronsted-Lowry definition of acids. And I told you I don't care if you remember the names of the definitions. This is the third definition, the Lewis definition. It's much less significant in general chemistry, but it is fairly significant in organic chemistry. And this class is supposed to prepare you for organic chemistry. So the Lewis model is looking at the transfer of an electron pair. The Bronsted-Lowry model focused on transferring a proton. The Lewis model focuses on the electron pair. So here, we should recognize, okay, well, NH3 is a base. This is a base. It accepts the proton. That's the Bronsted-Lowry definition. But we can also explain it in terms of the electrons. Here's this proton with no electrons. Here's the nitrogen, has a lone pair. We can think of the nitrogen as being very generous and saying, oh, you poor little thing, here, I'll share my electrons with you so you don't have to be alone, right? So both of these electrons in this bond came from nitrogen. Nitrogen is donating electrons to the hydrogen. A base is an electron pair donor. An acid is an electron pair acceptor. Great, another pair of opposites, right? One is the acid donates the proton, and the other is the base donates the electron pair. Urgh. Focus on remembering the Bronsted-Lowry definition where the acid donates the proton. And then when you come to a situation like this, you can identify which is the acid and which is the base. Here, the proton is the acid coming from an acid, and this is the base. It's accepting the proton. Okay, so identify that this is the base. Now, I'm going to ask myself, okay, what's happening with the electrons? Well, nitrogen had the electrons. In this interaction, nitrogen is donating electrons to hydrogen. So the base is the electron pair donor. It is a bit weird, a little bit confusing. Why do we need this definition? It expands the substances that can be considered acids. So in organic chemistry especially, we'll have interactions that are really acid-base reactions, but there's no hydrogen involved. And so then how do we identify which is which? A Lewis acid doesn't have to have hydrogen. With the other two definitions, you've got to have a hydrogen there, right, in order to form hydronium ion or to donate a proton. So here, NH3 is a base. It's a Bronsted-Lowry base. It's also a Lewis base. If you're a Bronsted-Lowry base, you're not going to be a Lewis acid. You're still going to be a base. It's just the definitions match up. So here, if we look at the interaction between BF3 and ammonia, BF3 is one of those guys where there's an incomplete octet on the boron. Boron only has, the Lewis structure for this is like this, and the fluorines have octets, and the boron does not. And why is that okay? Well, because boron is small and just sometimes goes along with that. Boron and beryllium will sometimes have incomplete octets, and we learned that in Chem 1A. So here's boron. Would boron like to have an octet? Sure it would. Here's nitrogen with its lone pair, and it says, oh, you don't have an octet. Why don't you come over here and I'll share my electrons with you, and now you can have an octet too. Nitrogen has donated electrons to boron. This is the base, this is the acid. When these two things come together, this is called an adduct. I'm not going to test you on that, but just if the word gets used, I don't want you to be confused. So Lewis acids are going to have an empty orbital, or they can rearrange their electrons to form an empty orbital that can accept the electron pair. So, as we saw with boron trifluoride, molecules with incomplete octets can act as Lewis acids. So here's AlCl3. Aluminum does not have a complete octet. It will be happy to come over with the nitrogen. The nitrogen shares 2 electrons with it, and here we go. So NH3 is acting as the base, donating the electrons. Aluminum is acting as the acid, accepting the electrons. Here's another one that, never would I expect you to look at that and say, oh, that's an acid-base reaction. That just looks confusing, doesn't it? Well, what's going on here? Well, here we have boron, this time with chlorine instead of fluorine, incomplete octet. And over here, we have this oxygen that has 2 lone pairs. The Lewis base is going to have some lone pairs, because that's what it donates. So this oxygen will donate this pair, sharing it with the boron to form this adduct. So this is, excuse me, this is the Lewis acid, and this is the Lewis base. This is not a huge deal in Chem 1B, but like I said, it will show up in OChem. Now this one's really, really kind of wild. So let's look at this. Here we have carbon dioxide, that's in the air, right? And water. So if carbon dioxide gets dissolved in water, this reaction can happen. It can also happen in the air, but not so much. And the water acts as the Lewis base, donates an electron pair to this carbon. Here, carbon dioxide is the Lewis acid. Well, carbon doesn't have an incomplete octet. It has an octet. It's got 2 double bonds. What's going on? Well, it can rearrange its electrons. So one of the pairs of electrons in this double bond can move over to the oxygen, which leaves an empty orbital for oxygen to bring its electrons in. And then these electrons are going to say, hey, I'll share with hydrogen, and hydrogen gives its electrons back to oxygen. And so we end up with carbonic acid. I don't expect you to understand that at all. This is the kind of thing that they get really into in organic chemistry. They talk about electrons moving around, and they draw a lot of curved arrows. Just if you want, a lot of people are asking me, what's OChem like? Is it harder or easier? It's different. It's very different. Any questions? We mentioned earlier that small, highly charged metal ions can act as acids. They are acting as Lewis acids. So here, Al3+, not with chlorines on it or anything, just the aluminum ion all by itself. It can accept electrons from water. So we form this adduct. It's a complex ion, aluminum and water in there. So this is the Lewis base, and that's the Lewis acid. And that's all we're going to say about that.